Hello, this is Gregory Maxwell, and this lesson is on quadratic functions and quadratic models. And of course, the PowerPoint presentation is using slides from Shauna Hayter from Salt Lake Community College. And so I'd like to give credit to her for what she's done. Today we'll talk about quadratic functions. And quadratic functions are functions of the form that are variations or transformations of the function y equal to x squared, which is represented by the red curve right here. It's an even function. It has one turn. The turn is called the vertex. This graph happens to open upward, so it has a minimum point. It passes through the origin 0, 0 at the vertex. And so that is the graph of y equal x squared. It's one of our fundamental graphs. So just as before I go in here, it would be good that you review your lessons on solving quadratic equations and the basic graphs of basic functions and the transformations of functions before continuing with this lesson. Now, a quadratic function is a variation or a transformation of this function y equal to x squared, or f of x equal to x squared, where f of x is the y coordinate. So the first thing we'll talk about is the first variation of a quadratic function, which is multiplying the x squared by a non-zero constant. So a function of the form f of x equal to ax squared, where a is either a positive number or a negative number. Now, if a is a positive number, the graph will remain opening upward, like this graph here, like the y equal to x graph, y equal to x squared graph, sorry. So if I have 3x squared, y equal to 3x squared, which is represented by this blue graph here, then the graph is still opening upward. And if I do y equal to 1/3 x squared, then the graph is also still opening upward. Forgive me, I need to make a quick correction. The blue graph is the graph of y equal to x squared, and the red graph is the graph of y equal to 3x squared. The green graph here is the graph of y equal to 1/3 x squared. Either way, once the coefficient of x squared is a positive number, the graph opens upward. We say that the graph is concave up. But if the coefficient of x squared is a negative number, such as y equal to negative x squared, which is really negative 1 times x squared, which is this blue graph here, or y equal to negative 3x squared, which is this red graph here, or y equal to negative 1/3 x squared, which is this green graph here, down here, those are going to have negative coefficients, so the graph opens downward, basically because it's just a reflection across the x-axis. Now, there's another adjustment that the a tells you. If a is a number that's bigger than 1, then the graph will actually get narrower because you're stretching the graph relative to the x-axis. So when you multiply by 3, for example, the graph actually rises more rapidly than it would if it's just y equal to x squared. So the graph ends up being narrower. But if you multiply the x squared by 1/3, the graph is not rising as quickly, so it gets wider. So when you're plugging a number, it lands at a lower point than it would normally be. So if you increase the size of the coefficient of x squared, then the graph will become more narrow. And if you decrease the size of the coefficient of x squared, then the graph will become wider. So 2 key points here, starting out with the graph of y equal to x squared, which is represented by this blue graph. If you multiply by a number greater than 1, a number that's greater than 0, a positive number, the graph will open upward. If you multiply the x squared by a number less than 0, the graph will open downward. If the number you're multiplying by is bigger in size than 1, the graph gets narrower. But if the number you're multiplying by is smaller in size than 1, then the graph gets wider. Now, this is an important form of a quadratic function. It's what I call vertex form. Vertex form. And because this form tells you the coordinates of the vertex as well as what the coefficient of x squared is, which is what we dealt with before. So this a in this form is the same a in the previous examples we just did, the previous form. So this is called vertex form. Some books call it standard form. I don't like to call it standard form because that confuses another form that is typically represented as standard form for polynomials. However, this is vertex form. It tells us the coefficient of x squared, which tells us whether the graph is opening upward or downward and whether it's narrower or wider than the standard graph. Then it also tells us the x-coordinate of the vertex and the y-coordinate of the vertex. H is the x-coordinate of the vertex, y and k is the y-coordinate of the vertex. H tells us how much the original graph is shifted to the right, and k tells us how much the graph is shifted upward. If h is a positive number, then of course we're shifting the graph of x squared to the right, h units. But if h is a negative number, we're shifting to the left. So, and if h is a positive number, then it's just x minus a number, such as x minus 3 or x minus 5. But if h is a negative number, you're subtracting a negative, so it will appear like x plus a number. So we're going to do a couple of examples to illustrate what we're talking about here. Let's start off with a function in what I call standard form. Y equal to ax squared plus bx plus c. A is the coefficient of x squared, b is the coefficient of x called the linear coefficient, and c is the constant. So in this case, a is 1, b is negative 6, and c is negative 1. What we want to do is rewrite this function in this form, from standard form here to vertex form here. That way we can tell a number of things that we can use for the graph. To do that, we will need to complete the square. And how do we complete the square? Very simple. We're going to separate the one by itself, and then we're going to add a number to this x squared minus 6x that will make it into a perfect square trinomial. But whatever I add to the expression, I must compensate by subtracting the same number. And if you may recall from completing the square, you take the coefficient of x, which is the linear coefficient, divide that number by 2 and square it, and that will give us what number should be added to the end here to make it into a perfect square. So when I divide negative 6 by 2, I get negative 3. When I square negative 3, I get 9. So I'm going to add 9 right here. And when I add 9, I will also subtract 9 to balance, to make sure that the net result is adding 0. What that allows me to do now is to take these first three terms and factor those and make them into x minus 3 times x minus 3, which is really x minus 3 squared. And then I'll just combine these two numbers, negative 1 minus 9, to give me negative 10. And now my function is in vertex form. A is 1, as was before. Same A that is here is the same A here. H is 3 because remember it's x minus h. So h is 3 and k is negative 10. So this graph is obtained by taking the graph of x squared, the standard graph, shifting it to the right 3 units because h is positive 3, and then shifting the graph downward 10 units because k is positive 10. So that's what we have for our transformation. We get to go from standard form, complete the square, and then we graph our function. Here's our function. We take the graph of x squared, shift it to the right 3 units and down 10 units. Now, let's take a look at a few other things that we can tell from this graph. So we can take the general quadratic equation, which I call the standard form, and convert that to vertex form. We can do that actually in a shortcut way instead of completing the square. In reality, it is a shorthand version of completing the square. Here's how we do that. You have a function in what I call standard form. Some books call this general form. I call it standard form. F of x equal to ax squared plus bx plus c. A is the coefficient of x squared, b is the coefficient of x, and c is a constant. This a is the same a in both expressions. To find the vertex, we need to find the coordinates of h and the coordinates of k. To find the coordinates of h is pretty simple. H is equal to negative b over 2a. That is a shortcut from completing the square. So remember now, a in this case is 1, b is -6, and c is -1. So my x-coordinate for my vertex, which is h, is equal to negative b over 2a. So I do negative of -6 divided by 2 times 1. And when I simplify that, I get 3. -6 is positive 6 divided by 2 is 3, which is what we got in our previous step, in our previous approach. Now, when we plug in the x-coordinate of the vertex into the function, we get the y-coordinate of the vertex, which is k. So I'm going to take this 3 and I plug it in to the function and see what we get. So we're going to do f of 3. So we get 3 squared minus 6 times 3 minus 1. 3 squared is 9 minus 18 is -9 minus 1 is -10. So just as we expected, we get our y coordinate for our vertex is -10. So hk is 3 comma -10, and those are the coordinates of the vertex of the quadratic function. Now let's take a little look at some other things that we might need. We might want to, for example, when we plot the vertex, we might want to tell the y-intercept. To find the y-intercept and the x-intercepts. So let's see, which one will we find first? Let's find our x-intercepts first. So I'm going to replace all my, oh, sorry, apologize for that. The axis of symmetry, that's very important. The quadratic function is symmetric about the line, about a line. In other words, there's a certain line that splits the graph in half. Half of the graph is on the left, half is on the right. That line is called the axis of symmetry. It is a vertical line that passes through the vertex of the graph of the quadratic function, which is called a parabola. So this axis of symmetry is a vertical line that passes through the vertex of the parabola, and it's a vertical line because the graph has to be opening upward or downward, otherwise we would not be dealing with a function, and we're talking about quadratic functions here. So the axis of symmetry then is x equal to whatever the x-coordinate of the vertex is. So the axis of symmetry is x equal to 3. It's a vertical line that passes through 3. Now, let's talk about the y-intercept. Where does the graph cross the y-axis? What we will do is then replace all our x's with 0 and see what we get for the y-coordinates. So we're finding f of 0. F of 0 is equal to 0 squared minus 6 times 0 minus 1, which is just a constant, -1. So since the graph is symmetric about the line x equal to 3, if I go 3 units to the left, plug in that x-coordinate, I will get the same answer as if I go 3 units to the right and plug in that x-coordinate. So 3 units to the left is the x-axis, 3 units to the right is the point x equal to 6. When I plug in 6, I should also get -1. Let's see. 6 squared is 36 minus 6 times 6. 36 minus 36 is 0 minus 1, -1. So the graph is going to give us the same result on either side. So now we have enough to draw the parabola. However, it is better to have additional points. So we want to find our intercepts, our x-intercepts. Let's find our x-intercepts here. To find our x-intercepts, we are going to replace all our y's with 0. And then we're going to solve the corresponding equation. Now this equation cannot be solved by factoring, so we'll solve it by using quadratic formula. So x is equal to -b plus or minus the square root of b squared minus 4ac divided by 2a. We plug in our a, b, and c as indicated. A is 1, b is -6, and c is -1. We plug them in, simplify, and these are our answers. 6 plus square root 40 over 2, or 6 minus square root 40 over 2. So those are approximately going to be 6.2 and -0.2. We plot those on the x-axis, and then we draw our graph to complete that. Of course, it will also pass through the other points as indicated. And there we have a graph of our quadratic function. Now let's talk a little bit about the maximum and minimum. So when we're trying to deal with mathematical models of a quadratic function, one key concept is the idea of a maximum and a minimum value of the function. In a quadratic function that opens upward, that means if the coefficient of x squared is a positive number, if a is a positive number, the graph opens upward, so it has a lowest point. So the graph has a minimum value. So when the graph opens upward, the graph has a minimum value. So when a is positive, the graph has a minimum. And then inversely, if a is negative, then the graph has a maximum value because now the graph opens downward. That also means that while the domain of a polynomial is all real numbers, so the domain of a quadratic function is all real numbers, the range of a quadratic depends on what the vertex is and whether there's a maximum or a minimum. If the vertex is a minimum value, then the range is that low k up to infinity. So in our previous example, the vertex was at 3, 10, negative 10, 3, negative 10. So the domain was all real numbers, but the range was negative 10 bracket all the way to infinity, because that's the lowest y value. In case of opening downward, the graph goes from negative infinity up to whatever the y coordinate of the vertex is, up to what k is. We will do some examples to illustrate this point. So before I do a few examples here, a couple of things I want to point out. So let's take a quick look at a quick summary here. And this summary, again, is from the book Pre-Calculus 5th edition by Blitzer. It's a quick review of the axis of symmetry. Is a vertical line that passes through the vertex. If the coefficient of x squared is positive, that is, if a is positive, the graph opens upward. If a is negative, the graph opens downward. We also know that if h is a positive number, then we're shifting to the right. If h is a negative number, we're shifting to the left. Vertex form, g of x is equal to a times x minus h squared plus k. And we can, of course, obtain h by doing negative b over 2a, and we obtain k by plugging in h into the function. Of course, if k is positive, we're shifting up. If k is negative, we're shifting downward. And then, if we want to get the equation from standard form, that, by the way, this is not standard form for us. We're going to call this form vertex form. So what I'm going to do here is that I'm going to do a little editing, and I'm going to replace that word standard with the word vertex, because vertex form indicates that we have the vertex of this function. So with vertex form, we have the a that tells us whether the graph opens upward or downward, whether how narrow it is, whether it's narrower than the standard or wider. The h tells us whether the graph is shifted to the right or the left, the graph of x squared, and k tells us whether the graph of x squared is shifted upward or downward. All right, what we want to do now is find those information and also the axis of symmetry, which is x equal to whatever h is. Find your x-intercept by plugging in 0 for y and solving for x. And find your y-intercept by plugging in 0 for x. In other words, finding f of 0. And then you plot all of those points. And if you need additional points, you need at least 3 points to plot the graph of a quadratic, and preferably more, such as 5. If you're given the function in standard form or general form, as some books may call it, what you do is you can do completing the square, or the shortcut is find h by doing negative b over 2a and then find k by substituting that into the function. And then, of course, we spoke about when you're graphing this function that you plot your necessary points and you connect those points together. Let's move on here. If you want to determine if the graph has a maximum or minimum, if a is positive, then the graph opens upward. such like in this form. So then you have a minimum, and the minimum is the vertex. The minimum point is the vertex. If A is positive, the graph opens downward, and then the graph has a maximum, which is also the vertex. So whether you're dealing with a minimum or a maximum point, though the point is the same, is indicated by the same quantity, the vertex, what tells whether it's a minimum or a maximum is whether the coefficient of x squared, A, is either positive or negative. Now, once we can determine that, we can now tell whether what the range of the function is, and that will also allow us to solve problems involving optimization, maximum and minimum value functions. We're going to do a quick example right now as an illustration as to how to do that. So let's take a quick look at this question here. The price P and the quantity X sold of a certain product obey the demand equation. The price is equal to negative half x plus 200, where x is the quantity, and the quantity sold is between 0 and 400 items. Express the revenue R as a function of x. Now, revenue is pretty simple. It's how many items you sell multiplied by the price per item. So if my price per item is $5 and I sell 10 items, then my revenue is $50. So generally speaking, multiply price by quantity will give us revenue. So R is equal to X times P. Now P is this function in terms of X. So I can replace all my P's with what X stands for. And that means now R is equal to negative half x squared plus 200x, which is what I got when I distributed the x into the parentheses. What we see here is that this is a quadratic function. And because it's a quadratic function, now we're talking about maximum value and minimum value. As you can see here, the coefficient of x squared is negative half, which means the graph has opens downward. Since the graph opens downward, then this revenue has a maximum value. So if we want to find a maximum value, we want to find out what quantity sold will give us that maximum value. And so we're going to find the vertex in that case. But before we do that, let's take a look at this. What is the revenue if 100 units are sold? X is the number of units. So simply put, to find the revenue when I sell 100 units, I just substitute 100 for X in the function and then solve. Evaluate. When I evaluate, I get $15,000. So the revenue brought in when 100 units are sold is $15,000. So now the question is, what quantity of X will maximize revenue? What they're asking is, what is the value of X that will give us the maximum value of R? Now, R is your Y value and X is your input. So really what they're asking for is the vertex, because that's where the maximum value occurs. So what we need to do is find our H value, which is our X coordinate for the vertex. H is equal to negative B over 2A. B is 200 and A is negative half. So when we find H, we do X is equal to negative B over 2A, which is 200 divided by negative 200 divided by 2 times negative half. So we end up with 200 over 1, which is 200. So if we sell 200 items, that will give us the maximum revenue we can get. What is that maximum revenue? Well, simply plug in 200 in for X. When I plug in 200 for X, that works out to be $20,000. So the maximum possible revenue I can obtain from this model is $20,000, not 200,000, sorry, $20,000, and that will occur when we sell 200 items. So 200 is the X coordinate of the vertex, and 20,000 is the Y coordinate of the vertex, and the Y coordinate tells us the maximum value. And we know it's a maximum because the X squared has a coefficient that is negative. Continue with the same example here. What price should the company charge to receive the maximum revenue? Well, we know the maximum revenue occurs at 200 items sold. So all I have to do is plug in 200 for X, and that will give me $100. So I need to sell each item for $100. Okay, so let's get back to the examples here. Now that we have seen an example of the use of the quadratic function in a model situation, we're going to spend the rest of the lesson here doing examples. We're going to spend some time doing examples. First example, use the vertex and intercepts to sketch the graph of the of each quadratic function. Give the equation of the parabola's axis of symmetry and use the graph to determine the domain of the range. Now the domain is a simple thing. If it's a quadratic function, it's a polynomial. The domain is always all real numbers. But first, let's identify what we're dealing with here. If you notice, this function is actually in vertex form already. So I'm just going to indicate that the function is in vertex form. And in this case, it's the a is 1, and then of course vertex form gives you h is 3 and k is 2, because vertex form, as you recall, is a times x minus h squared plus k. And so you see the k is 2, h is 3, and a is 1. Now, since the graph already is in vertex form, we don't need to do much work. We just have to analyze what we have. So right away, we see that since a is a positive number, the graph opens upward. And because the graph opens upward, then we know that we have a minimum value for the graph. And what I would recommend you do is, since you know the graph opens upward, just do a little rough sketch of what that will look like. So I'll just draw a little parabola that opens upward, and that will tell me that I'm dealing with a minimum value because the vertex is the lowest point on the graph. So then right away we know that the vertex has coordinates 3, 2, and that the vertex is a minimum point on the graph. The minimum value is 2 and it occurs at 3. Now, that means then we can tell what the axis of symmetry is. The axis of symmetry, by the way, is not a number, it's a straight line. So you need to write the equation of the line. X equals to 3. That's it, axis of symmetry. Let me write the words out. Axis of symmetry. I'm writing all the word symmetry here, but in future, I will just write an abbreviation for it. X equals to 3. The axis of symmetry is not 3. That's just a number. The axis of symmetry is the line x equal to 3. That's a whole line. So you need to make sure you indicate that it's x equal to a number, not just a number. Now, then we know what the domain of the graph is. I don't need the graph actually to do the domain. The domain of a quadratic function is always all real numbers unless there's an artificial restriction. And then the range now is important. The range starts from a lowest point because the graph opens upward, so it has a minimum. The lowest point is the y-coordinate of the vertex, which is k, 2, and then the graph rises forever, so it goes up to infinity, and that's the range. Now let's see if we can find the y-intercept. To find the y-intercept, I just simplified f of 0. F of 0 is equal to 0 minus 3 squared plus 2. And I see that that's 9 plus 2, which is 11. So the y-intercept is at the point 0, 11, which is quite interesting since the graph has a y-intercept that's the graph has a range that's from 2 to infinity, and it opens upward, which means the graph doesn't dip lower than 2. The graph doesn't cross the x-axis. So this graph will not have any x-intercepts. Let's do a little quick sketch and see what that would look like. So first of all, I'm going to draw my axes. I put it's not going to be drawn to scale, but general rough sketch. That's my vertex. And then Not quite drawn to scale as I said, but you get the idea. That's what the graph generally looks like. Again, not drawn to scale. There's a little bit of not quite symmetric. Now, the axis of symmetry, which I will draw with this red line, is a vertical line that goes through the vertex. So the axis of symmetry here should pass through the vertex. So I'll just write that now as x equal to 3. The vertex here has coordinates 3, 2. The y-intercept is at 11. And as you can see here, the graph has no x-intercept because it does not cross or touch the x-axis. And that's that. Let's move on to the next example. And now I would like you to try this on your own. Just remember to get it in vertex form. So try it on your own, then you can check my solution. So the first thing I will do is rewrite the equation in vertex form by solving for y. Y equals to x minus 1 squared, and then I'm going to add 3 to both sides to get the 3 from the left side to the right side. And again, you see that this equation is still in vertex form. So I don't need to do any work to convert it to vertex form. The equation is already in vertex form. So a is a coefficient of the parentheses, which is 1. H, since this is in vertex form, we talk about h and k. So h is positive 1 and k is positive 3. So let us go through this process again quickly. As before, the graph opens upward, again because a is greater than 1. Greater than 0. A is a positive number. And that means if I were to do a rough sketch of this graph, it would be a parabola that opens upward, which means again we will have a minimum point. Then the vertex, therefore, will have coordinates 1, 3, and that would be a minimum point. The axis of symmetry then will be the vertical line that passes through the vertex, and that's x equal to the h. X equal to h. The domain of a parabola, of a quadratic function, is all real numbers because there's no domain restriction. And the range, since this graph has a minimum point, the minimum value of the graph is at 1. Not at 1, sorry. The minimum value is 3, and it rises to infinity. Now the y-intercept, of course, we obtain by plugging in 0 for x. So that's y equals to 0, 0 minus 1 squared, which is 1, plus 3, which gives us 4. So the y-intercept is 0, 4. Now, if I try to find the x-intercept, here's what I would do. To find the x-intercept, I'll replace the y with 0, and I would solve for x. Now, this I can solve by PEMDAS. There's only one x variable in a quadratic, so I just get rid of the weakest link, subtract 3 from both sides, and then find the square root of both sides. And when I do that, if I subtract 3 from both sides, I get a negative 3. So I end up with plus or minus square root of negative 3. That does not give us a real number answer. So since this gives us no real number solution, then we know that there is no x-intercept. So we have no x-intercept. No x-intercept. So our graph is going to look pretty similar to what we just did. So that's just confirmation for the process here. I'm going to draw my axes, and I'll draw my parabola. My axis of symmetry. And of course, my vertex here is 1, 3. My y-intercept is at 4. And my axis of symmetry is x is equal to 1. And there we have that. Now let's go to something a little bit more challenging. In this example here, this still looks like vertex form. It just looks a little backwards. So let me rewrite this. I'm going to rewrite this as f of x is equal to negative parentheses x minus half squared plus 5 over 4. Now in this case now, a, this is still in vertex form. A is now -1, h is now half, and k is now 5 over 4. Now, since a is a negative number, the graph opens downward. Graph opens downward. And so, the graph has a maximum value. The graph has a maximum value. Let's draw a little quick sketch of what it will look like. And so we're talking about a maximum. So let's see what the vertex is. Vertex has coordinates half, 5 over 4. And that's a maximum point on the graph. So then the axis of symmetry is x equal to 1/2. And then, of course, the domain is -infinity to infinity. And the range, now the range here doesn't start at 5/4 and go upward. In fact, that's the highest point. The range comes down from -infinity, and the highest point it goes up to is 5 over 4. So the range now is written this form, -infinity to 5 over 4 with a bracket, because it's a closed endpoint. So now the y-intercept, as always, we plug in 0 for x. So we have 5 over 4 minus 0 minus half squared. Now 5 over 1, 0 minus half is -1/2 squared is 1/4. 5/4 minus 1/4 is 4 over 4. So the answer here is 1. So the y-intercept then is at the point 0, 1. To find the x-intercepts, if there are any, we replace f of x with 0, and then we solve for x. And we can solve this by doing 0 property, by reverse PEMDAS, subtract 5 over 4 from both sides, and divide both sides by -1, and then square root both sides. And then add a half to both sides. So I have half plus or minus the square root of 5 divided by 2. and those are my endpoints. Now they are approximately equal to, those values are equal to, if you do it on your calculator, negative 0.618 and positive 1.618. It's 3 decimal places. So my x-intercepts, which I'll write the x-axis value here, my x-intercepts are half minus square root 5 over 2, comma 0, and half plus square root 5 over 2, comma 0. And these, of course, tells us what those approximate values are. Now let's take a look at the graph, see what the graph looks like. I'll have a shorter graph here because of space. Let's see if we can fit it in. So right away we see that the graph has a positive and negative x-intercept, and it crosses to the point 1, and opens downward, so the graph looks something like this. Not exactly neatly drawn, but you get the idea. And then the axis of symmetry, let me see if I can do a little bit attempt again at drawing a better graph here. So third attempt. Slightly better, but not by much. Let's hope that is not too much of a problem. Okay, so our axis of symmetry passes through the vertex, and of course that equation is the line x equal to half. And then my vertex here is the point half comma 1 half comma 5/4, which is 1 1/4. And then this point here is the point, that point there, let me use a different color. That's my x-intercept is 1/2 plus square root 5 over 2, and that one there is 1/2 minus square root 5 over 2, and then this intercept is at 1. And that's the graph. Now let's go to this one here. Now this one clearly is not standard form. Clearly not standard form. So let's see what we can do with this one. First of all, well, it's not vertex form, sorry. What we'll do is rewrite this so that it's in standard form. F of x is equal to negative x squared minus 4x plus 5. So I write it in decreasing powers of x. This is in standard form, as I call it, or as some books call it, / general form. And in this case, we get a, which is -1, b, which is the coefficient of x, and c, which is 5, the constant. We do not know h and k as yet, but we do know that the graph opens downward because a is negative. So we know right away that that's that. So let's see the vertex. Let's find out what the vertex is. To find the vertex, we need to find h, and h is -b divided by 2a. In this case, -4 divided by 2 times -1. So that gives us -2. Then we find k by plugging that value of h into the function. So f of negative 2 is 5 minus 4 times negative 2 minus the square of negative 2. And C, 5 plus 8 plus 4. Sorry, 5 plus 8 minus 4 is equal to 9. So 5 plus 8 is 13, and then minus 4 is 9. So my vertex then has coordinates negative 2, comma 9. And the graph is this is a maximum value because a is less than 0. And just to remind us what we mean here, that means the graph opens downward. Now, let's talk a little bit about the axis of symmetry. That's easy. Axis of symmetry is just x equal to the coefficient, the x coordinate of the vertex. And the domain, of course, is all real numbers. Negative infinity to infinity. And the range is, since it's a maximum, it starts from negative infinity and rises all the way up to the y coordinates of the vertex. And then we can now determine our y-intercept, which in this case is pretty simple because all you have to do is replace all your x's with 0, and that will cause only 5 to be remaining. So we have 5 minus 0, 4 times 0 minus 0 squared, which is equal to 5. So my y-intercept is 0, comma 5. Now let's see if we can find the x-intercepts. X-intercept is 0 is equal to 5 minus 4. Well, let me rewrite it the other way. Negative x squared minus 4x plus 5. And if I divide both sides by negative 1, I get 0 equal to x squared plus 4x minus 5. And that one actually can be factored. 0 is equal to x minus 1 times x plus 5. See, because negative 1 times 5 is negative 5, and negative 1 plus 5 is 4. So that means my two x-intercepts are x equal to negative 5 and x is equal to 1. So we have negative 5 comma 0 and 1 comma 0 as my x-intercepts. Now let's see if we can draw this graph. First we draw our axes. X-intercepts are at negative 5 and 1. Vertex is at 2, 9. Y-intercept is at 5. So we're looking at a graph that looks something like this. The axis of symmetry is the line x equal to negative 2. And the y-intercept is at 5. X-intercepts are at 1 and negative 5, which are evenly spaced from the axis of symmetry 4 units away. 3 units away, sorry. And that's that. And there we have it. Let me put the vertex here. Negative 2,9. Few more examples to go. In this case, function is in standard form, but the coefficient of x squared is a number bigger than 1. So again, this function is in standard form. In this case, a is 2, b is negative 7, and c is negative 4. Now we know that the graph opens upward, so we have a minimum because a is positive. So I'm going to draw a little sketch to remind us what the graph looks like. So we know we're going to have a minimum. And let's find our vertex. To find our vertex, this is in standard form or general form. So we do h, which is negative b divided by 2 times a, which is negative of negative 7 divided by 2 times 2, which is 7 over 4. Now to find k, we simply do f of h, f of 7 over 4. And that is 2 times square of 7 over 4 squared minus 7 times 7 over 4 minus 4. You can just plug that into your calculator and you'll see that that works out to be negative 81 over 8. So then our vertex then has coordinates 7/4, comma, negative 81 over 8, which is negative 10 1/8. And that point is a minimum point. So now we know that the axis of symmetry is. The axis of symmetry is x equal to 7 over 4. X equal to the x-coordinate of the vertex. The domain then is simple. Negative infinity to infinity. The range, since this is a minimum, this function has a minimum, the range starts at the negative 81 over 8, the k, and rises to infinity. Now let's talk a little bit about our y and x intercepts. So to find my y-intercept, I'm going to do f of 0, and as you can see, that will work out pretty simply to be negative 4. So my y-intercept is 0, comma, negative 4. Now to find the x-intercept, you're going to replace f of x with 0 and solve the quadratic equation, which in this case, it may be factorable. Negative 7 squared is 49. 4 times negative 4 times 2 is negative 32. And 49 plus 32 is 81. So that does work out to be a perfect square. So this can be factored. Nevertheless, I'm going to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. Plugging that into the function, I get, into the formula, I get negative 7 plus or minus the square root of the square of negative 7 minus 4 times 2 times negative 4. And then all of that divided by 2 times 2. So that means x is equal to 7 plus or minus square root 81 divided by 4. So x is equal to 7 minus 9 over 4, which is negative half, or x is equal to 7 plus 9 over 4, which is equal to 4. So my x-intercepts are negative half comma 0 and 4 comma 0. Let's do a quick sketch, see what that looks like. So graph opens upward, minimum point, the vertex is 7/4 and negative 81 over 8, which is about negative 10 and 1/8. Y-intercept is at negative 4. So let's see if we can, that's about approximate. It's not exactly neat, but you get the idea. This point is negative 4. This point is negative half. This point is 4. Axis of symmetry. The axis of symmetry is x equals to seven-fourths, which is the x-coordinate of the vertex. And that is our function. So, as always, I strongly recommend that you keep practicing these questions so that you get used to doing them. Khan Academy is a great place to do those. Now, let's do a few applications. We'll do about 4 examples here, and then that will be the lesson. Question says, a ball is thrown upward and outward from a height of 6 feet. The height of the ball, f of x, is in feet, can be modeled by the equation f of x is equal to negative 0.8x squared plus 3.2x plus 6, where x is the ball's horizontal distance. So x is how much the ball moves to the right or left, and f of x is how high the ball goes. Both are measured in feet. And that's the height, this is the distance from where the ball is thrown. A, what is the maximum height of the ball and how far from where it is thrown does this occur? B, how far does the ball travel horizontally before hitting the ground again? And C, graph the function, the path. So let's start off. I usually like to draw the graph to illustrate, but we don't need that right now. So for part A, they're asking for the maximum height and where it occurs. Maximum height occurs at the vertex. So they're asking for the vertex. So we have to figure out the vertex here. This equation is in standard form. We know that A is negative, so we know that the graph opens downward. That's why they're asking for the maximum height. All right, so we're definitely going to need to know the vertex here. So for part A, and we're going to say H, A is equal to negative 0.8, B is equal to 3.2, and C is equal to 6. So to find our vertex, we do H is equal to negative B divided by 2A, which is negative 3.2 divided by 2 times negative 0.8. That will give us negative 3.2 divided by negative 1.6, which is just positive 2. And then K is what we get when we plug in the value of H. So we do negative 0.8 times the square of 2 plus 3.2 times 2 and then plus 6. And that's 6 plus 3.2, which is 9.6. 9.2. And so the vertex being 2 comma, so the vertex is 2 comma 9.2. We then know that the maximum height is the y coordinate of the vertex, and the x coordinate is where that occurs. So for part A, maximum height is 9.2 feet, and it occurs at 2 feet at 2 feet, which is the h, from where the ball is thrown. There we have it. Now let's do part B. Part B, they say, how far does the ball travel horizontally before hitting the ground? Now, if the ball hits the ground, what is its height? Its height is 0 feet above the ground. They want us to round the answer to the nearest foot. So the height is equal to 0. So f of x, which is the height, is equal to 0, which means 0 is equal to negative 0.8 x squared plus 3.2 x plus 6. We're going to solve that quadratic equation. Now, to make our life simpler, what I am going to do is divide everything by negative 0.2. That will get rid of our decimals. So divide by negative point, well, let's do negative 0.4. So if I divide everything by negative 0.4, 0 divided by negative 0.4 is 0. Negative 0.8 divided by negative 0.4 is positive 2 x squared. Positive 3.2 divided by negative 0.4 is negative 8. Of course, x. And then 6 divided by negative 0.4 is actually negative 15. So then I can use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. Which is negative 8 plus or minus the square root of negative 8 squared minus 4 times 2 times negative 15. All of that divided by 2 times 2. Working that out, we get x is equal to positive 8 plus or minus the square root of. It's you work out under the radical, you get 136 over 4. And that gives us two possibilities for x. X is either equal to negative 0.915, which you can work on the calculator, or positive 4.915. Now, since you're measuring from start, a negative distance means you went backwards, but we're moving forward here. So then the answer for part B is 4.9 feet when the ball hits the ground. So that's the answer for part B. And then finally, to graph the function, let's see what we have here. Let's graph this model to represent what we're dealing with. That's the ground, and that represents the height. And when we start throwing, we see that the initial height is 0, because when x is 0, y is 6, so the initial height is not 0, 6. Ball gets thrown upward, reaches the maximum height, and then comes downward to where it hits the ground. hits the ground at a point 4.9 approximately. Height thrown is 6, and the maximum height occurs at 2 feet from where it's thrown. The maximum height is at 9.2 feet. And there we have it. Let's do 3 more examples, and that will be it. Among all pairs of numbers whose sum is 20, find a pair whose product is as large as possible. So, and what is that maximum product? Let's say we have the 2 numbers here. I'm going to call one number x and the other one w. The reason I don't want to use y is because y can be confused for the y coordinate of the equation, which we're going to obtain. So, to avoid that confusion, I'm going to say, well, we know that the sum of, I'm going to use a different variable, sorry, and then the sum of those variables is 20, so x plus w is 20. I'm going to call p the product. So the product is xw. So if I replace, I can rearrange this equation so that w is equal to 20 minus x. Why would I want to do that? What I want to do that for is to take that w minus that 20 minus x and replace w in the product formula. And the reason I want to do that is because they're telling us about a maximum product. Maximum product means that's my function that I'm going to find the maximum value for. And so I need to find an equation for that that would look quadratic at least. So when I replace w with 20 minus x and work that out, I get p is equal to negative x squared plus 20x. I just distribute the parentheses and rearrange it into standard form. Now what that does then is tell me that my vertex, let's write that up here, A is -1, B is 20, and C is 0. So my vertex then is H equals to negative B over 2A, which is negative 20 over 2 times -1, which is 10. And K is P of 10, which is negative 10 squared plus 20 times 10, which is 100. Well, so what does that tell me? So one number has to be 10, and the other number has to be 10. So x is equal to 10, which means w has to be 20 minus 10, which is 10. So the two numbers are 10 and a 10. And the maximum product is what you get when you multiply those, which is what our K was, is 100. Take a little moment to go through that example carefully. You may rewind the video to see what I did. Let's go through this example here. Among all pairs of numbers whose difference is 24, find a pair whose product is as small as possible. That means they want the least product. And what is that minimum product? Now, as small as possible is a misleading term here. We want it to not be as small as possible. I'm going to change that wording a bit because it can be a little ambiguous. And instead of saying as small as possible, I'm going to instead say as low as possible. Because low now is not referring to size, it's actually referring to pardon me here, it's actually referring to position relative to the number 0. So it's as low as possible. So let's see if that will work. All right, so let's see what we have. So for this one here, again, we need the two numbers. I'm still going to use the two variables x and w, again, because I don't want to confuse the y, x, w. So let's say we do w minus x is 24. So that means w is x plus 24. Because they said their difference is 24. So one minus the other. So let's just choose w as the larger number or the greater number. W minus x is 24. We also know that their product, again, is equal to x times w, which I can now replace that with x times x plus w plus 24. When I do that, I now have the equation p of x is equal to x squared plus 24x. That's a quadratic function with a coefficient of x squared is 1, so it's a minimum. And of course, that's why they ask for a minimum. And as always, we do our vertex. A is 1, B is 24, C is 0. H is negative b over 2a. So that's negative 24 over 2 times 1. It's negative 12. And then, of course, that's my x coordinates. So that would be x. So x is equal to negative 12, which means w is negative 12 plus 24, which is positive 12. So one number is negative 12 and the other one number is positive 12. So the numbers are negative 12 and positive 12, and the minimum product is negative 12 times 12, which is negative 144, which would be the answer we had gotten if we had plugged in negative 12 here. Negative 12 squared is 144, plus 24 times negative 12 is negative 288, and that would have given us negative 144. So those are our answers. Last example, and that will be it for the lesson. You have 600 feet of fencing to enclose a rectangular plot that borders a river. And if you do not fence the side along the river, find the length and width of the plot that will maximize the area. And what is that largest area? And so we see that there's a little diagram here that illustrates what they're talking about, and they even did some extra work for us. They filled in this region here. I'm going to redraw that graph just so we can have an idea of how they got that 600 minus 2x. So what we have here is we have a rectangular region, which I will now draw basically like this. So that's the rectangular region. One part of it is covered by a river, so we don't have any fence for that side. Let's call this piece X and that piece X. That's the part that's perpendicular to the river. And then since the whole length is 600, the rest is 600 minus the 2 x's that you used over here. So then the area is length times width. Remember that. It's a rectangle. Length times width. So the area then is 600 minus 2x multiplied by x. If I distribute that and simplify, we end up with the area, and since the area is in terms of x, a of x is equal to negative 2x squared plus 600x. So they want to find the plot that will maximize the area. Since we're maximizing the area, we need to find the vertex of this graph. So to find our vertex, we know the vertex is h equal to negative b over 2a. And we already know that b is 600, so it's negative 600 divided by 2 times negative 2. And 600 divided by 4, which is 150. So x has to be 150. So then the perpendicular side, the side that's perpendicular to the river, side that is perpendicular to the river is 150 feet. And the side that's parallel to the river, which is the other side, is going to be 600 minus 2 times 150, which is equal to 300 feet. And so the dimensions then are 150 feet by 300 feet. And of course, the 150 feet is perpendicular to river. And 300 feet is parallel to the river. And of course, it's pretty simple to see what the maximum area is. Maximum area is just length times width. Maximum area is equal to 150 times 300, which is equal to 45,000 square feet. And that brings us to the end of this exercise. Of course, there's a lot of work that you will need to do. As always, I strongly recommend that you watch Khan Academy videos for additional support and do those exercises on Khan Academy. They are very good exercises to do. And additionally, as I recommend the openstacks.org, they have a good website with a free open source math textbook and other textbooks as well. You can find a college algebra textbook. They have free exercise there, and you can also see the app. So you can use OpenStax, OPENSTAX.org, or you can use the OpenStax app, and you can also use Khan Academy for additional practice. All the best. Keep practicing, keep working, and do well.